the fact that phi hat t of u, norm of this is 1. So for claim 3, we need to show that at of x minus at of y is less than or equal to x minus y for all x and y in pt of x. So there are only two cases. If at of y is equal to sigma c inverse, then at of x is less than sigma c inverse, and at of x minus at of y is less than 0. And otherwise, at of y is equal to d of y and x, excluding py, and at of x is less than d of x and x, excluding pt. So implies that at of x minus at of y is less than or equal to the distance between x and x, excluding pt of x, minus distance between y and x, excluding pt and y, which is less than x minus y, since pt of x is pt of y. They are in the same cluster. And so I want to introduce another embedding, which I've briefly mentioned before in my previous lectures. And I mean, people like now are interested in these things because you embed it into a Banach space. And as I said, Banach space is a geometric space. You can do all kinds of functional analysis that you like, because most of the functional analysis of the theories of functional analysis is well developed for vector spaces, not just any norm space, not just any metric space. It is a vector space, and you can do many things. So the simplest thing that you know is it's a linear algebra, but you know functional analysis is much more general than that. But the embedding that I want to say is Kuratowski embedding, which is I from x and rho to the and rho is your metric, and to the that vector space with a special norm. So Kuratowski was interesting because he said that we can embed it into L infinity by just look at each point as a function. Rho, z, and y. Z is a constant. This is fixed. This is inside x bar and fixed. Also, we don't need this one, but we use it just to make it sure that it is bounded. But in general, we don't need that even. So this is in the space of L infinity of x, and L infinity is a very bad space. LP space is L little p. I mean, L little p is much better than L big L with infinity, and because it's a very bad space, and I will show you what can you do to make it more useful. For example, the problems with Kuratowski embedding is that you cannot do some kind of differentiation as you do in many different spaces, and you should create your own differential and differential things, and all you need to do for finding the quotients and doing algebraic algebraic stuff. And so the norm of kx of x minus kx of x tilde, I want to show that this is x and x tilde. You can prove it by just draw a simple triangle y, x, and x tilde, and do triangular inequality, which is what? Which is rho x, x tilde plus rho x tilde and y. This is greater than rho of x and y. So now you know that rho of x and y minus rho of x tilde and y is less than rho of x and x tilde. So I've proved this one. So now you know that this guy is a member of L infinity, but some people, it is better to do better construction. So kx of x, like anything else, you can do restriction. The idea is from restriction. So you can do the same things, the same embedding, but now you can just focus on D domain. So that's how you have successfully embedded to L infinity of D, and the closure of D is X, closure of X, and the idea of Gromov-Hausdorff convergence of metric spaces is like this. And for example, X is separable. We have an inclusion into L infinity. And a theorem of Hausdorff-Gromov says that if K1 and K2 are subset of X and rho, which is a closed subspace, of course, then the Hausdorff distance is defined by the distance of that K1 and K2 subset. This is infimum of K1 subset K1, which is inside the ball of with epsilon radius of K2, and this is and K2 is a subset of epsilon ball of K1. And you know that when I say epsilon ball, I mean all x where distance of x and m is your manifold, is less than equal to epsilon. And so, very interestingly, we have defined a metric, but now with very nice properties. So this L infinity norm is a metric, and by Ascoli, we can say that all K inside X1 is compact if X is so. Is compact if X is so. So the second part is that if K1 and K2 are in the same metric space, take infimum of distances of I1 of K1 and I2 of K2, where Ij is a map from that space Kj with metric rho j into. So we have a very big metric space, and we decompose it to very little metric spaces as we do in partitioning. So you now see the ideas. So this is the isometric mapping, and the C is that using Kx, a family of xi and rho I, as I said, like a partition with many metric spaces are pre-compact in Gromov-Hausdorff distance. This says that uniformly bounded equicompact and supremum of diameter of x1 is of all of xi is less than infinity, because kx maps all kx I and rho I into the compact subset of L infinity. And you know that L infinity of x has the property that if y is inside z and sigma, of course that is a theorem, and it is L Lipschitz. Then F has L Lipschitz extension. All of these extensions are ideas in functional analysis, if you're not familiar with that. Extension to all of Z. So we do something, we find a functional, for example, with a very small space, for example, W, and then we extend it to the general space, X. So you generalize that whatever you have, a functional or whatever you have, to the general space. This is the idea of functional analysis, and the name of that that extension is just McShane extension, and some people call it infimum convolution. So f of z is infimum of f of y plus L rho z and y for all y in y. And in order to understand these things, there is a book, Metric Embedding, that about 400 pages. If you read this book, you will see all of the ideas of Gromov-Hausdorff, how Kuratowski embedding is useful, how can you use Banach space theories for a metric on graph, something that you don't see in many of the articles. And because it is very hard, because you should be both a mathematician and a computer scientist. Something like Nauer. Nauer is very smart guy because he's now a mathematician, because he's a very big mathematician, and also he knows exact problems in computer science, and so he can bridge the gap between mathematics, pure mathematics, and computer science, which is very applied. So we need people like Nauer. For example, Nauer talks about Ribe program, and those things that you need to see what is the application of that. But the best thing is start from Kuratowski embedding, because it embeds everything to Banach space, and then after that is just functional analysis. And then you go back to the original space, original metric space on your graph with shortest path, geodesics, and as a metric, and then do some analysis. So it's like an inverse problem. You go to the Banach space, it is easy because it's geometric, it has nice properties, and you do quotient things, you make new spaces, and then you come back to your original graph G is equal to V and edges, and with a metric D, and then do the analysis. So it's like a reverse engineering, because B, your Banach space, is easy to handle. And research on metric embedding is very interesting, because you can create many groups, like people in India and people in Israel are very active on that, to combine mathematicians with computer scientists. And I haven't seen anywhere else, but I want to introduce two organizations in the world that are, I think it is my opinion that these two organizations are the best organizations for theoretical machine learning and also computer science and statistics. for applications in real problems that humanity needs, such as protein folding, such as genetics, such as making vaccine for coronavirus, and all things that people really need. Not just building some weapons that people don't even need that, and just it destroys humanity. So Max Planck and Indria. Max Planck, people like Bernard Sholkov, I like him very much because he extends and generalizes the notions, the concepts of kernels, and the theory of kernels in machine learning is very practical in machine learning. Also in Indria, it is a very great group by people like Bach, and also some people that developed compressive machine learning, which generalizes the ideas of compressive sensing. And if you combine these Max Planck theories in machine learning, uses kernels, to ideas in Indria, which uses kind of random projections, sketching, and metric embeddings, then we have a very, very powerful idea, much more powerful than deep learning, which is very naive, because people do deep learning and it doesn't even use, deep learning doesn't use maybe less than 1% of mathematics, but metric embedding, I haven't seen anything more useful than this, because this is the modern theory of dimension reduction. So dimension reduction, things like LLE and those things, manifold learning, all of them are special cases of metric embedding. And also, if you do the metric embedding, something like random projection, even your calculation is so fast because principal component analysis and all of them, they cannot scalable. Even if you use robust PCA, which claims that it has reduced the problems of robustness and robust statistics, but still you cannot scale it because it takes too much time. It prone to many problems. But metric embedding is a well structured thing. It has more than 500 years of history, and you can use many great powerful things. But only researchers in Israel and France have contributed in that. But we have 140 countries. We need all of them, all of these countries to contribute on metric embedding, which is just the future of machine learning. And it can be much more successful than deep learning, which is just a calculator and doesn't have any meaning. But when you find a similarity between the points in a graph, you see what a powerful metric you have, the shortest path. And it's very natural because, for example, you can extend these theories to make your machine learning more scalable. But deep learning is not scalable, although many people do advertisement, but it doesn't use any kind of rigorous mathematics, in my opinion. Okay, thank you so much.